If you place a paramagnetic material on a lab bench, it looks completely inert. But at the atomic level, it is the site of a continuous, invisible battle between two competing forces of nature. The first force is the applied external magnetic field. When this field is turned on, it attempts to force billions of tiny atomic dipoles into strict, uniform alignment. This diagram illustrates the conflict. On the left side, the magnetic field pushes for order. On the right, we see the opposing force, thermal motion. Ambient heat acts like a violent wind, constantly randomizing and scrambling the alignment of those same dipoles. The temperature dictates which force wins. At high temperatures, the heat energy is severe. This thermal chaos dominates the system, scrambling the dipoles so thoroughly that the material exhibits very low net alignment. But as the material cools, the thermal wind dies off. At low temperatures, the external magnetic field faces less resistance, successfully aligning the moments to create a large, measurable magnetic response. When we measure a material's magnetic susceptibility in a lab, we are reading the real-time score of this thermodynamic tug-of-war. We can model the exact outcome of this battle using a mathematical principle known as Curie's law. This graph maps the relationship clearly. Magnetic susceptibility, represented by the Greek letter chi, falls inversely with absolute temperature. As the temperature disruptor gets larger, the magnetic response drops off. Looking at the equation, the denominator accounts for the thermal disruption. The numerator holds the crucial proportionality factor, the Curie constant, labeled C. The Curie constant is the specific value that sets the magnitude of that curve. It isolates the exact amount of paramagnetic response that remains after we factor out the temperature, measuring the total strength of the independent magnetic moments available to align with a field. But an abstract number only gets us so far. To understand what the Curie constant physically measures, we have to bridge the gap between macroscopic lab data and the quantum properties of individual atoms. To derive Curie's law mathematically from first principles, we have to start at the scale of a single atom seeking its lowest possible energy state. Precise. This first panel shows an individual magnetic dipole, labeled mu. When an external magnetic field, B, is applied, the dipole naturally seeks its lowest energy state by pointing its moment directly along that field line. If the lab were at absolute zero, every atom would line up perfectly. But any real-world environment contains thermal energy that knocks these atoms off axis. To build our model, we use the weak field approximation. As shown on this scale, we establish a condition where the randomizing thermal energy, the Boltzmann constant times temperature, heavily outweighs the magnetic alignment energy. Because the thermal energy is so overwhelmingly large, the external magnetic field can only slightly bias the population of atoms toward alignment. It lacks the power to completely overcome the random thermal distribution. As this third panel illustrates, when we scale this weak perturbation across millions of atoms, the total magnetization of the material becomes linearly proportional to the applied field divided by the temperature. Susceptibility is defined by how much magnetization you get for a given applied field. It's simply m divided by h. By dividing out the applied field from our linear relationship, the equation distills down to the inverse temperature dependence. Susceptibility equals a constant over T. We've arrived at Curie's law. That remaining constant value sitting in the numerator dictates the slope of the curve, containing the entirety of the material's inherent magnetic strength. If C sets the overall scale of a material's magnetic response, what precise physical variables inside the metal actually dictate its value? There are exactly two. The first is number density. Look at pillar 1 on this graphic. Increasing the concentration of magnetic ions per unit volume naturally increases the total bulk response of the material. More magnets equal more pull. The second physical variable is moment strength. Over in pillar 2, we see the alternative path. Even if the density of atoms remains constant, swapping in a material composed of atoms with intrinsically larger individual magnetic moments will yield a much higher Curie constant. This microscopic equation binds both pillars together. The Curie constant equals the vacuum permeability times the number density, n, multiplied by the effective magnetic moment squared, all divided by 3 times the Boltzmann constant. Notice the mathematical scaling. The number density scales linearly. If you double the number of magnetic atoms, you double the Curie constant. But the effective magnetic moment is squared. Because moment strength scales quadratically, the intrinsic power of the individual atom dictates the macroscopic magnetic limits of the material far more aggressively than how many atoms you can pack into a box. The Curie constant is often introduced as a simple thermodynamic scaling factor. However, this classical view is incomplete, as it cannot explain the physical origin of the magnetic moment's strength. That quadratic variable, the effective magnetic moment driving the entire equation, is actually dictated by quantum mechanics. This formula reveals what actually dictates the effective moment. It is rooted in a specific quantum parameter labeled J. J represents the total angular momentum quantum number of the specific magnetic ion you are testing. Physically, J is the combined sum of the inherent spin of the atom's electrons and their orbital motion around the nucleus. The G, sitting at the front of the equation, is the Landé G factor. It acts as the coupling metric, a calculated value dictating exactly how that specific spin and orbital motion interact with one another. A moment of clarity. Because the Curie constant contains this effective moment, its value is anchored to the angular momentum of the electrons. Measuring the bulk thermodynamic susceptibility of a metal in a laboratory is actually reading the invisible quantum architecture of its atoms. So, how do material scientists physically extract this quantum information in a practical laboratory setting? The standard procedure starts by placing a sample in a magnetometer and recording its magnetic susceptibility across a wide range of decreasing temperatures. Once the raw decay curve is plotted, scientists apply a simple mathematical transformation. They take the reciprocal of the measured susceptibility. By plotting the inverse of susceptibility against temperature on this graph, the math transforms a curved decay slope into a perfect straight line. By calculating the slope of this line, we can determine the Curie constant directly, since the slope is equal to 1 divided by c. Now, up to this point, Curie's law relies on an assumption. It models an ideal paramagnet, where the individual magnetic moments never interact with each other. But in complex solid-state materials, moments are packed tightly together. They exert forces on their neighbors, requiring a necessary modification to the math. This is where the Curie-Weiss law kicks over. To account for interacting moments, the denominator is upgraded from a standalone t to t minus theta. That new variable, theta, is the Weiss temperature. It acts as a dedicated parameter that captures the strength and the nature of the magnetic interactions between neighboring atoms. By fitting lab data to this upgraded Curie-Weiss equation, scientists successfully disentangle the raw size of an atom's quantum moment, represented by c, from how it behaves with its neighbors, captured by theta. Whether modeling an ideal gas or characterizing a heavy rare earth magnet, the Curie constant remains the unique material-specific signature of any paramagnet. This diagram maps the entire connection. The constant serves as a mathematical bridge, locking two different scales of physics together. At the macro level, we input the simplest variables a laboratory can provide, temperature and bulk susceptibility, and through the constant, we extract precise microscopic truths, the volumetric density of the atoms, and the hidden quantum power of their coupled electrons. Ultimately, the Curie constant serves as the functional link between these two scales, translating the discrete rules of quantum angular momentum into the magnetic behavior we observe in the lab.